And the kinematic equations, concept related to motion and the kinematic equations. If we talk about the magnitude numeric value of displacement and compare that to distance, contrasting displacement and distance. Displacement is in a straight line. Distance traveled, we can go around curves. So if you think of this, we have some route that is perhaps this shape. I would record the distance along all the curves that are there, but the displacement would go from where we end back to where we start for that line. If it's a vector, and displacement is a vector, then I draw it like this if we're starting here. So what do you think? The magnitude, not the direction. Distance doesn't have a direction, but what about the magnitude of the displacement? This straight line compared to going around all the curves. And hopefully you say smaller than. Usually displacement will be smaller than the distance traveled. When would there be an exception? Well, if the motion's along a straight line and the motion is always in one direction, though the object is not retracing its steps, so to speak. If the motion's in a straight line and continuously off to the right or continuously off to the left, the magnitude of the displacement would equal the magnitude of the distance in that situation. Okay, number 2 here. We've got Ed driving a car from Fremont, Nebraska, in the central United States, to St. Louis, Missouri, and watching the odometer in the car. It happens to go over 20,000 as a reading during the trip, and Ed was noting the odometer at the start and at the end, did a subtraction, and he found there was 473 miles along the road from Fremont, Nebraska to St. Louis, Missouri. What does the odometer of a car report? It's not the speed. It doesn't have using miles per hour. It's just miles. Is it distance or is it displacement? Is it acceleration? No, it's not meters per second squared. Well, what about comparing distance and displacement? Now, does the odometer advance as you go around corners? Yes, and it's just distance. The odometer does not give you displacement. The road from Fremont, Nebraska to St. Louis, Missouri is not a straight line. Okay, the equation x, position, equals velocity multiplied by time, only gives the correct x when v is a constant, when the velocity is a constant. What do you think about that? It is true. It is true. In this situation, this is really distance equals rate times time that you may have heard of. Distance equals rate times time. If we make x naught equal to 0, then our final position equal to velocity times time. We must have a constant here to use this simple formula. The kinematic equations handle the case of acceleration and a little bit more complicated formula. So for distance equals rate times time, be very careful that you know that the velocity is a constant, that your rate is a constant. Okay, the 4 kinematic equations, not going to write them down here. In what situation are we not allowed to use them? Well, we can have a change in position. The kinematic equations allow us to calculate the new position based on the old position, velocity, and acceleration. Are we disqualified from using if velocity changes? No, that's okay. The kinematic equations show us how to calculate the change in velocity. Can the acceleration change? No. So C is the answer here. To use the kinematic equations, you must have constant acceleration. If the acceleration changes from one constant value to another constant value, you'll have to do 2 calculations. One calculation for the first value of acceleration, and then pick up the data and inputs into the calculation for the second part. Speed is allowed to change. That's just the magnitude of velocity. So, next one here, true or false one. The selection of the value of x naught is critical, the initial position when time is equal to 0. It's critical because the selection of the location of the 0 location will change the calculated values, give us a different concept of what's happening in the problem. So, perhaps I pick this kinematic equation, x equals x naught plus 1/2 final velocity plus initial velocity multiplied by the time interval. Now, am I going to be in trouble if I don't really think about it and make the correct choice for where x naught is equal to 0, or what the x naught value is? The answer is no, I will not be in trouble. And this equation really is giving us the change in location. If I move the x naught off to the left side, 1/2 v plus v naught and t. Some people call this distance. It's really displacement. So we're moving just the x-axis here in a straight line. It's equal to this distance, but a little better to call it displacement. It doesn't matter if I have x naught equal to 0, when time is equal to 0, and perhaps I get 20 here for these numbers. Well, that's fine. If I happen to say x naught is 5, I'll get 25. The difference will be 20. So it's probably to your advantage. Go ahead and choose a starting location that the x naught value is 0. The position is 0 when the time is equal to 0. But you've got some freedom to make the choice of the value of x naught when time is equal to 0. Okay, here we've got a ball that's near the surface of the Earth. It's moving vertically away from the Earth, so it's a straight line vertical motion. And I'm going to draw this here. So we've got the ball going upward. It reaches a high point, and then of course it's going to come back down to the Earth. But we start here, we come up to this high point, and that's where this problem is focusing on. There's some time to get to this maximum height. When it's at the maximum height and it's not going to go any higher, well, the velocity is 0 up here. What's true about the acceleration? The ball started with some velocity upward. We threw it upward. It goes to a certain height in a certain time. Not going to bother to calculate those. The velocity is 0 at the top. What do you think the value of the acceleration is? And just the magnitude of the acceleration. Over the years, many students have selected 0. That is not correct. If the acceleration was 0 and the velocity was 0, this ball would not move. It would stay up here with velocity of 0. If the acceleration is 0, the velocity doesn't change. And the answer is still, if we don't go too far away from the surface of the Earth, 9.8 meters per second squared will be the value. People cannot throw a baseball or football to a height where the acceleration due to gravity is significantly different than 9.8. So we'll have 9.8 up here for problems that are in the environment near the surface of the Earth. You should keep 9.8 every place along the motion, and this acceleration will be minus 9.8 meters per second squared, and the acceleration will be directed towards the Earth. So don't, again, fall into a trap here. The velocity is 0, but the velocity does not control acceleration. Velocity never controls acceleration. The acceleration determines how the velocity changes over time. So 9.8 meters per second squared, that's the magnitude of the acceleration. It is directed towards the ground. I usually work problems where the up direction is positive, so I assign minus 9.8 meters per second squared to the acceleration due to gravity. So ask your instructor, ask your fellow students, keep practicing on the concepts of kinematic equations.